Hey everyone, welcome to today's Explainer. Calling all mechanical and civil engineering technology students, get ready, because today we're tackling an absolute cornerstone of your coursework, engineering statics. We're going to master force vectors, and more importantly, we're going to conquer those complex bolt problems together. If you've ever stared at a totally chaotic diagram of forces and wondered where on earth to even begin, well, you're in exactly the right place. I am super excited to guide you through this step by step, so let's dive right in. Here's our game plan for today. First, we'll hit Section 1, Vectors and Force Fundamentals. Then, Section 2 covers components and unit vectors. After that, we'll move into Section 3, adding forces for equilibrium, and finally, the main event in Section 4, solving bolt force problems. We're building this really logically, starting from the basic theory and working right up to applied problem solving. To get started, I want you to picture the real-world applications here. Think about a massive construction crane lifting heavy concrete structures high into the air. Before you can build at that kind of incredible scale, you absolutely have to understand how abstract mathematical forces act upon physical joints. Every single cable, every beam, and every bolt is experiencing force. And if those forces aren't perfectly balanced, what we call equilibrium, things literally fall apart. So getting a handle on these vectors, it's not just some math exercise, it's literally the foundation for building safe, real-world structures. All right, Section 1, Vectors and Force Fundamentals. To satisfy your course learning outcomes, we really need to get our basic definitions crystal clear.
In statics, you're mostly going to be dealing with two broad categories of vectors, fixed and free. Fixed vectors do exactly what they sound like. They define a point's location relative to a fixed origin, or they represent moments of force about a very specific axis. They're anchored. On the flip side, free vectors can be applied anywhere without changing their overall effect. The velocity of a moving car, that's a free vector. And crucially for us today, forces acting on a particle are also free vectors. This is exactly why we can slide a force along its line of action. Another really cool example of a free vector is a couple. That's when two equal and opposite forces create pure rotation. There's no fixed application point, just a defined direction and magnitude.
Okay, let's lock that theory in with a rapid-fire knowledge check. First up, what defines a position vector? Think back? Right, it's a fixed vector defining a point relative to a specific origin. Next is velocity a fixed or free vector? It's a free vector. Finally, what creates pure rotation with no fixed application point? That would be a couple. Awesome job. Let's keep this momentum going.
Moving right along to Section 2, Components and Unit Vectors. So, we know what forces are, but to actually analyze them mathematically, we have to break them down into digestible pieces. Imagine you've got a force vector, let's call it F, acting at an angle, theta. We can resolve the single-angled vector into perfectly perpendicular components, essentially drawing a perfect rectangle. We call these Fx and Fy, which are your rectangular vector components. Honestly, this is the absolute secret weapon of statics. You're taking one awkward angled line and turning it into two nice, neat straight lines right along your axes. Now to express these mathematically, we bring in our unit vectors, I and j. They are perfectly perpendicular to one another. The I vector runs perfectly parallel to the x-axis, and the j vector runs parallel to the y-axis. But the single most important thing to remember about them? They have a magnitude of exactly 1. Literally just 1. They purely exist to give our math a sense of direction. So how do we put this all together? Well, vector components are expressed as the product of those directional unit vectors and the scalar magnitudes. So your force in the x direction becomes Fx times the unit vector I, and your force in the y direction becomes Fy times the unit vector j. Just Fx and Fy on their own are your scalar components, the raw numbers. But the second you attach the I and j, boom, you've got your full rectangular vector components. All right, time for quiz number 2. Let's see what you've got. First, what do we call Fx and Fy? Those are your rectangular vector components. Second, what is the exact magnitude of a unit vector? It's exactly 1. Third, which axis does the unit vector I run parallel to? That's the x-axis. And finally, what axis does j parallel? The y-axis. Excellent. You've officially got the mathematical vocabulary you need for the hard stuff. Let's hit Section 3, Adding Forces for Equilibrium. Knowing how to break one force down is super helpful, but let's be real. In actual structural analysis, you never just have one force. Take a look at a typical joint. We might have 3 forces. Let's call them P, Q, and S, all acting concurrently through a single point, point A.
Because these forces are coming in from all different angles and aren't parallel, we can't just do simple addition. If we want to figure out the overall effect these three forces are having on that point, we must resolve them into their components using 2D or 3D analysis first.
So, here is your golden checklist, your universal rule for 2D force addition. Step 1. Resolve every single force into its rectangular components using sines and cosines. Step 2. Sum all the corresponding x scalar components together. Step 3. Sum all the corresponding y scalar components together. See? It's incredibly systematic. Once you've summed up all your x components and all your y components, you get the components of your resultant vector, which we label r. The scalar components of this resultant vector are exactly equal to the sum of the individual forces' scalar components you literally just calculated. After that, you just use some simple trigonometry to find the final magnitude and direction of r. It's like putting a puzzle together.
Okay, let's pause for a quick knowledge check before we hit the heavy math. How do we add non-parallel forces? Right, we have to resolve them into components first. And what equals the sum of those scalar components? The scalar components of the resultant vector. Finally, in the statics of particles, can these forces act through different points? No way. They are always concurrent at one single point.
All right, here we go. We've made it to the main event, Section 4, Solving Bolt Force Problems. This is where we apply everything we just talked about to actual step-by-step engineering scenarios.
Let's recap the strategy specifically for these bolt problems so you have a solid mental map. First, resolve each force on the bolt into its rectangular components. Next, add your x and y components together to find the resultant components. Finally, use trig to calculate the final magnitude and direction. Keep this three-step checklist in mind as we tackle our first big scenario.
Check out how this strategy completely tames what looks like visual chaos. We've got 4 distinct forces yanking on bolt A. But if you look closely at the math, we just take force 1 and break it into F1 cosine 30i and F1 sine 30j. Then we do the exact same thing for force 2 using 20 degrees, force 3, and force 4 using 15 degrees. By simply converting everything into sines and cosines along the x and y axes, we just transformed a totally overwhelming 4-force problem into a really straightforward addition problem.
Let's look at another super common scenario. We have a bolt at point A, but this time only 2 forces are acting on it. Force P at 40 newtons pulling at a 20-degree angle, and force Q at 60 newtons pulling at an additional 25-degree angle. Now, because there are exactly 2 forces here, we actually have a choice of 2 distinct methodologies we can use to find the resultant.
As future engineers, you really need to master both of these approaches. The first is the graphical solution. For this one, you basically construct a parallelogram to scale, where the sides are parallel to forces P and Q. The diagonal of that parallelogram represents your resultant force, which you can physically measure. The second approach is the trigonometric solution. This one is way more precise. You use the triangle rule for vector addition, combined with the law of cosines to find the exact magnitude, and the law of sines to find the exact angle.
Awesome work keeping up with all this math. Let's hit our final knowledge check for today. What is step 1 for complex bolt problems? You always resolve every force into rectangular components first. Next, what geometric shape is drawn to scale in a graphical solution? That'd be a parallelogram. And lastly, which specific mathematical laws are used in the trigonometric solution? You'll need the law of cosines and the law of sines. Well, we've covered a ton of ground today, mastering 2D Cartesian vectors and applying equations of equilibrium to particle statics. But before we wrap up, I want to leave you with a little something to chew on. If everything we did today on a 2D plane relies on unit vectors I and j, what happens to our math when we bring in a z-axis to look at a fully animated 3D structural view? I mean, what happens when we introduce the k-vector? How does that change our equilibrium equations? Think about it, because that 3D perspective is exactly where your syllabus is taking you next. Thanks so much for learning with me today. Keep practicing those bolt problems, and I'll catch you in the next explainer.